Good afternoon and good evening to all my friends across Region 10. We are into the 10th edition of R10 Talk, the popular event of Region 10. And today's topic is reliability and safety challenges for the AI hardware to enable the future Metaverse. And speaker is none other than Dr. Cecilia Metra from Italy. For the inaugural session, we have with us Professor Kook-Jin Chun, and it's my privilege to introduce him at the start. Professor Kook-Jin Chun is a past director of Region 10, as well as a past vice president VP at MGA. Professor Kook-Jin Chun received PhD degree from the University of Michigan in 1986 and had been teaching in the Seoul National University in Korea for over 30 years. He has served the ECE department as head and now a professor emeritus in the same. He is a fellow of IEEE and received the Order of Merit in Science and Technology from the Korean government. With these words, I would request Professor Kook-Jin Chun to kindly deliver the welcome address and introduce today's speaker to the audience. Over to Professor Kook-Jin.
Good afternoon, everybody. Today we'll have a talk on the Metaverse, which is a very hot topic these days. The technology, as I understand, involves VR, AR, and sensors, and the increasing immersion with haptic devices and AI. And today we are very lucky to hear from the most leading researcher on this topic, the Cecilia Metra from Italy. She is a professor and the deputy president of the School of Engineering at the University of Bologna, where she has worked since 1991. And she is now serving as IEEE Division 5 Director, and she was the president of the IEEE Computer Society in 2019. We know that the Computer Society is the biggest society among 39 societies in IEEE. She is co-chair of the IEEE Metaverse project of the IEEE Future Directions Committee and a member of the IEEE Conference and IEEE Award Committees. She was editor-in-chief of the IEEE Transactions on Emerging Topics in Computing and the associate editor-in-chief of the IEEE Transactions on Computers. She published extensively on international journals and conferences proceedings on design for testability, reliable, safe, secure, and resilient circuits and systems, and trustworthy AI circuits and systems. She's an IEEE Fellow, IEEE Computer Society Golden Core member, and a member of the IEEE Honor Society, HKN. So again, we welcome Cecilia Metra, and so we'll have a talk. We'll listen to her. So Cecilia, the floor is yours.
Thank you very much. I will start sharing slides. So, okay, so can you please confirm you can see my slides, right?
Yes, we can see. Yes,
okay, so thank you very much. Good morning, good afternoon, and good evening, depending on time zone. Thank you very much, Professor Chan, for the introduction, for the kind introduction. And also I would like to thank the Region 10 Director, Professor Lan Fung, the past Director of Region 10, Dr. Deepak Mathur, and the Region 10 Director-elect, Professor Takako Hashimoto, for the invitation. It's really a great pleasure and honor for me to deliver this talk at Region 10. And we will talk together about reliability and safety challenges for the AI hardware to enable the future Metaverse. As already mentioned in the kind introduction of Professor Chon, I'm a professor at the University of Bologna in Italy. I was the president of Computer Society in 2019, and I'm at the last year of my service as IEEE Director for Division 5. So the Metaverse, as we know, we are starting hearing a lot about it these days, can be envisioned as a new layer bridging the gap between the digital and the real world. And today we already have a huge variety of tools, for instance, enabling a very accurate digital emulation of the real world, for instance, for product design, or an augmented reality experience, for instance, for educational purposes, or natural language interaction with a virtual assistant, for instance, for work support, or the creation of a digital twin of a real entity, for instance, for predictive maintenance, or to provide financial services using the blockchain technology, and much more. And the future metaverse should include and connect all these already existing but still separated capabilities into a unified environment, consisting of interoperable digital and real worlds with inclusive accessibility to all. And the expectations are that by the year 2030, the value of the metaverse could reach approximately the $5 trillion. And these $5 trillion will include use cases from companies in a large variety of application fields, including, of course, entertainment, social communication, but also healthcare. And there is the expectation of significant adoption of the metaverse in healthcare, and including also product manufacturing, including, for instance, the production of our electronic devices, and much more. And the expectations are that the metaverse will reach a mature state by the year 2030. So artificial intelligence will be a key technology to enable the metaverse by providing the human interaction with the metaverse, for instance, through natural language communication and gesture recognition. It will enable object detection in images and videos. Also, AI will enable a personalized experience in the metaverse, for instance, based on personal preferences, possible disabilities, and so on. So given the key role played by AI to enable and to access the future metaverse, and given the expectations of widespread, I would say, adoption of the metaverse in different application fields, of course, the question about the reliability and safety of AI arises. And as we know, by definition, reliability is the ability to guarantee the continuous delivery of the intended so correct service for a given amount of time, while safety is the ability to guarantee the absence of catastrophic consequences on the environment and users in case of misbehaviors. And nowadays, we are talking a lot about the trustworthiness and safety of AI, mainly from the point of view of its social and ethical implications. We are worried about the fairness and inclusiveness of the data used to train AI. We worry about data privacy and protection. We are also concerned about the explainability of AI and about the liability of decisions taken based on AI. And all of these are, of course, major issues. And as developers of the technology, we can, of course, contribute to the solution and to address these issues. But I believe that we cannot solve them alone, because these big issues mandate regulations at the legal and governmental level. But assuming and hoping, since there is a lot of activity in this field, also at the governmental level, that these issues will soon be regulated and so, let's say, properly addressed and solved. To guarantee the reliability and safety of AI, we need also to be able to guarantee the reliability and safety of the hardware that is executing the AI. And this is our responsibility, since we are the ones who develop such a technology. And this because we know that the hardware can be affected by faults and aging conditions during its operation in the field. And this could put at risk the reliability of the AI and the safety of the system that is using the AI. as we will see in a few minutes with more specific examples. But let us start from the faults and aging conditions that could affect our hardware that is used to implement AI. So from the point of view of faults, it is known that a big concern for current scaled down electronic technology is due to the possible occurrence of the so-called transient faults that could affect the hardware during its operation in the field. And these transient faults may be due to, for instance, alpha particles that, as we know, are atoms of helium that lost the electron, that can be generated due to the radioactive decay of unstable isotopes present within the packages, or they may be due to neutrons, for instance, generated by the collision of galactic cosmic rays and atmosphere atoms, mainly nitrogen and oxygen. And when these energetic particles hit the silicon substrate of an electronic circuit, we could assist to the modification of the voltage value associated to a circuit node, so that an undesired, very fast transition of the voltage value associated to a circuit node takes place, which is what we call a transient fault. And the problem is that if, for instance, a transient faults affect a node within the combinational part of, for instance, a data path, or for instance, another accelerator that is used to execute AI, what happens is that if this transient fault that is locally generated propagates till the input of a memory of a latching elements, as a simple flip-flop at the end of the data path, depending on the spike that we have at the input of the flip-flop, and depending on the instant, on the sampling edge of the clock for the flip-flop, and depending on the setup and hold time of the flip-flop, well, at the end of at the output of the flip-flop, we can assist to the generation of a logical error, which is typically referred to as soft error. So we could have incorrect data within our hardware that is, for instance, executing AI, with consequent risk for the reliability of AI and safety of the system. How much likely is it that this can occur? There is a lot of research in this field. I also personally worked on this at the University of Bologna together with my collaborators. And we cannot neglect the likelihood, the possibility of occurrence of this event. But the generation of soft errors due to transient faults is definitely much more likely if the node affected by transient fault is the node within a sampling element, just like a latch in this picture, or a memory cell. And particularly, we have shown that the node prior to before the feedback loop of a latching element is the one that, if affected by transient fault, has the highest probability to give rise to an output of error. So this is likely. There is a lot of research in the field in the past as well as right now to develop approach to make memory elements robust with respect to this kind of event. So due to soft errors, transient faults, a soft error may be generated at the output of a latching element or in a memory cell. So again, we could have incorrect data within our hardware that is implementing AI, with consequent risk for the high reliability and safety. In addition, also aging is of major concern nowadays for currently scaling down technologies. As we know, also electronic circuit age with time, and particularly the bias temperature instability is one of the most likely aging phenomena for currently scaling down technologies, and is one of the aging phenomena of major concern. And BTI can take the form of negative bias temperature instability if it affects PMOS transistors, or positive bias temperature instability if it affects NMOS transistors. And if we consider, for instance, MBTI, this causes an increase in the absolute value of the conduction threshold of PMOS transistors. Consequently, the conductance of the transistor will diminish, and consequently, we will have a slowdown of the operation of the circuit that is including these transistors. And so we have a performance degradation at the circuit level. And it has been proven that this performance degradation can be higher than the 20% in 10 years of operation. Then when the transistor is turned off, there is a recovery, but this is only a partial recovery. And another issue is that we cannot predict basically, or let's say it's very difficult to predict which transistors will be more impacted by aging than the others, because this depends on the activity of the transistors, and so on the application that is running on the hardware. So this is the problem of aging. Aging may cause a possible violation of timing constraints of our circuit, and as a consequence, again, we could have the sample of incorrect data within our circuit, and so again, we could have a risk for the reliability of the eye if this aging is involving the hardware that is used to implement the eye. And also we could have risk for the safety at the system level. And in addition, recently in this paper in collaboration with Professor Rossi from University of Pisa, Professor Romagna from University of Bologna, and Professor Pacagnella from University of Padua, we have shown years ago that bias temperature instability may increase the likelihood that if a circuit node is affected by transient fault, it gives rise to an output of error. So aging is making integrated circuit more vulnerable to generate, more likely to generate soft errors when affected by transient faults, which is a problem we just discussed. And if we now consider the specific case of hardware implementing AI, for instance, hardware accelerators, we have found that if aging affects the transistors in the data paths of hardware accelerators implementing neural networks, we have verified that the data path propagation delay may increase of almost 35% over a considered 5-year operation time. So due to aging, we could assist to the incorrect operation in the field of the hardware accelerator that is implementing AI, with consequent risk for the high reliability and safety at the system level. And what about soft errors? Already in 2017, in this paper, it was proven that if soft errors affect the memory elements of hardware accelerators implementing deep neural networks used, for instance, for image recognition on an autonomous vehicle, it was shown that if the memory elements affected by soft errors are those containing the neural network weights, and particularly the exponent of the weights, we could have a possible misclassification of images. And in this paper, it was indicated that a track may be misinterpreted, misclassified, as if it were a bird. So that, of course, the actions taken at the level of the autonomous vehicle would have been quite different. And so due to the soft errors affecting the memory elements of hardware accelerators containing the weights of the neural network for image recognition, the AI may work incorrectly, so may be unreliable, and we could have a serious risk for the safety of our system. We also did some analysis concerning the occurrence of soft errors affecting neural networks used for another purpose, which is to monitor the state of health of batteries, for instance, adopted to power portable devices for medical applications. And we found that if soft errors affect the memory elements of hardware accelerators implementing neural networks, used to monitor the state of health of batteries. Again, if the memory elements affected by soft errors are those containing the neural network weights, up to 17% of degraded batteries are erroneously recognized as non-degraded. With consequent, so in this case, of course, the AI is not reliable, making a wrong, let's say, conclusion that these batteries are in good health while they are not. And we could have, of course, a safety risk at the system level, for instance, if these batteries are used for portable biomedical applications. And this is a more recent research that we done in collaboration again with Professor Romagna from the University of Bologna, engineer Sara Creti from University of Bologna, and Gianni Borelli from the Beghelli company. And again, for another kind of application of AI, we have verified that in this paper that has been recently published, that soft errors again affect memory elements of hardware accelerators, implementing, in this case, autoencoders that is known as a particular kind of neural networks that are frequently used to detect unauthorized messages generated during cyber attacks. If the memory elements, again affected by soft errors, are those containing the autoencoded weights, in this case, we found out that up to 79% of legal transactions are erroneously recognized as illegal, so that such transactions are inhibited. So in this case, of course, our, let's say, AI is not reliable, and we have risk for the system availability. So in this case, security is not impacted because actually also legal transactions are erroneously recognized as illegal, and so they are inhibited. But of course, the system becomes unavailable, and the AI that is adopted for security purposes is not working in a reliable way. And this is a research that we conducted again in collaboration with Professor Romagna from the University of Bologna, and also Dr. Finelli, that at that time was at the University of Bologna. And so what can we do? So we have seen that we have risk for the high reliability in case of soft errors affecting the memory elements of hardware accelerators that are implementing AI. In case they are affected, these memory elements, and particularly those containing the weights, in case they are affected by soft errors, could cause the unreliable operation of the AI. So which one can be a possible solution? So in order to protect memory elements with respect to soft errors, we know that we can use error correcting codes. This is a solution that is widely adopted to protect the cache of microprocessor, to protect any memory. And in order to implement ECC, we have to use some additional hardware. They can also be implementing only via software, but quite often we prefer to implement additional hardware to add ECC in order to minimize the memory latency and so on. And in this figure, we have an example at the block level of the hardware that is needed to implement a single error correction, double error detection ECC, and of the hardware needed to implement a double error correction error correcting code. This additional hardware that is needed to implement ECC has been till recently assumed for free. And this because the area occupied by these blocks is significantly lower than the area occupied by the memory array. So the idea and the concept was that it was much more likely that soft errors or other kind of faults could affect the memory array than these additional blocks. But recently, within a research partially supported by an Intel Corporation research grant, we started analyzing the possible effects due to faults that may also affect these additional blocks that are needed to implement ECC. And this in the perspective of their adoption for a widespread set of applications, first of all, autonomous systems. And what we found out is that, for instance, if if resistive bridging faults affect the additional hardware that can be used to implement ECC to protect memories against of errors, we found out that due to these faults possibly affecting this additional hardware, the ECC technique may fail in correcting an incorrect word memorized in the memory, with the generation of an indication of achieved correction, so that at the system level, we have no way, unless we modify this structure, to realize that a problem occurred. Or also, due to these faults affecting the additional hardware needed to implement ECC, a correct word memorized in the memory could be erroneously changed. So that at the end, we have an incorrect word, incorrect not because of faults affecting the memory cells, but because of faults affecting the hardware that is used to implement a technique to protect the memory cells with respect to faults, again with an indication of no error in the word read from the cache. So, due to faults affecting the additional hardware that is typically adopted to implement ECC, which are a well-known approach to protect memories with respect to soft errors, the ECC approach may be non-effective in protecting actually the memory due to faults affecting this additional hardware itself, or even in addition to this, due to faults affecting this additional hardware, we may make wrong a word that instead was correctly memorized in the memory. And so if we are thinking about using this approach for to protect the memory cells containing the weights of neural networks implementing AI, we could have risk for the reliability of the AI and for the system safety. And in this paper, which is currently under review, which is co-authored by Professor Romagna from University of Bologna, Engineer Manfredi, who was at the University of Bologna at the time of the research, and Dr. Locatelli, Dr. Chiavacci, and Dr. Petrucci from Intercorporation, we, of course, present also a possible solution in order to guarantee that with ECC, we can protect memories with respect to soft errors, and that at least if there are faults affecting this additional hardware, we are able to realize that, so that at the system level, we can try to implement some technique to address this issue. So with these solutions and others that are under research to protect the additional hardware needed to implement ECC, ECC could be actually an approach to protect the memory cells containing the weights of neural networks in order to avoid the risk for reliability of the AI due to faults affecting the AI hardware in the field. But this may also not be a solution in some cases. For instance, recently, we addressed the case of resistive memories that, as we know, are promising to be adopted for in-memory computing that could accelerate furthermore the execution of AI, and especially in the perspective of the use of AI as an enabler for the metaverse. Of course, the speed of AI execution and computation is very important. And we analyze what happens if we have faults affecting these resistive memories. And we found out that if we have a bridging fault, as we know, is a fault that may occur during the operation of the hardware in the field, which is basically creating a conductive path between two lines or nodes that should be isolated. This may be due to electromigration that is very likely to occur in the field when we are in the presence of high current density and high temperatures. And we found out that if a bridging fault affects for instance, a single cell selector, these bridging faults affecting a single cell selector can affect the datum written to or read from a large number of memory cells, where this large can be up to 64 numbers in our analysis, up to 64 cells sharing the same word line. And now, if we think about 64 errors, this is definitely a multiplicity of errors that cannot be corrected at a sustainable cost using ECC. So for this kind of, so in this case, ECC cannot be a sustainable solutions, and a new solution should be devised in order to protect resistive memories with respect to possible bridging faults affecting the selectors of these resistive memories. And so in order to guarantee the AI reliability if these memories are used for in-memory computing for hardware accelerators. And in this recent publication that is co-authored by Professor Romagna from University of Bologna and Sejudi Bardan, that at the time of the research was at the University of Bologna, also presents a possible solution to this problem. So, in conclusion, we have, of course, we need to guarantee, in order to guarantee a trustworthy AI, that also the hardware executing the AI is reliable and safe. And the reliability and safety risk for the hardware executing the AI are part of the technological challenges that we are addressing also within the IEEE Metaverse initiative of the IEEE Future Directions. And for those of you who may be interested in the technical challenges behind the Metaverse, whether for its social, let's say, application and for its industrial application, please join us at this link so that we can share some activities that we are doing as part of this Future Direction initiative. So to conclude my presentation, AI will be a key technology to enable the future metaverse. And the future metaverse is predicted to receive to reach a very significant financial value by 2030, and to include use case adoption for a huge variety of companies working in a widespread spectrum of application fields. And given this, let's say, key role played by AI to enable the accessibility and the inclusive accessibility to the metaverse, of course, the problem of the reliability and the safety of the AI arise. We are talking a lot about this issue nowadays, also from the point of view of the ethical and societal implications of AI. And I believe these are very important issues that need regulations at the governmental and legal level that, as far as I know, are coming. And but in addition to this, in order to guarantee the reliability and safety of AI, we would need to be able to guarantee that the hardware implementing the AI is reliable and safe. And there are some open issues that I try to address and to mention today. There are lots of solutions that are currently under research. There is also the development of specific standards in the field. And so hopefully all these issues will soon be solved so that highly reliable and safe AI hardware will soon become a reality to enable a future metaverse with an inclusive accessibility to all, and hopefully it will help to improve our society and environment and make our world and life better. So that's all for my presentation. Thank you very much for your attention.
We will have a quick question answer session. We have some questions in the chat box. I will just one question is, ma'am, wouldn't triple redundancy and voting circuits take care of soft errors?
I'm trying, sorry, to read the questions myself.
The question is, wouldn't triple redundancy and voting circuits take care of soft errors?
Thank you. This is a very good question. Yes, TMRC, triple modular redundant systems, are a solution that on principle enables to take care of errors. There are, I said on principle because from the implementation point of view, there are some issues. So the first issue is that, as you may know, these replicated modules needs to be diverse to really be able to provide high reliability, because otherwise there is the risk of the so-called common mode failures. And the diversity, which typically arises to the point where you need to have diverse implementations, in the sense, for instance, microprocessors from different companies, comes together with some synchronization issues and, of course, with significant cost issues. And in addition, there is also the still, I would say, under-researched issue of the reliability of the voter. Because again, if we think about the widespread application of the AI, and so consequently the criticality of the reliability of and the liability also of the decision taken by AI, we need to guarantee high reliability. And so high reliability for the hardware implementing AI. Triplication and voting can be a solution, but then we need to be sure that this solution is really solving the problem. And so also the voter reliability is of concern. So we need to make sure that the voter is highly reliable itself. And in addition, we need to make sure that we use diverse replicas of the same module to avoid common mode failures. And all of this together comes out with some challenges from the research point of view, and of course some cost issues. But this is also a possible solution, and other solutions in line with this that are under research are also partial triplications of some parts. So if you're able to figure it out, which are the most, for instance, critical parts in a complex neural network that are more likely to give rise to problems if affected by soft errors, you may even think about some partial triplication. And so this is a very good question, and this is also one of the solutions that are under considerations, of course, with the, let's say, from the cost point of view, with the implication that I just recalled. But thank you very much. It's a very good question. I see another question. I don't know if you want me to answer.
Can you hear me, ma'am?
Yes, no, before it was not.
What role does electromigration play in old circuits?
Yes. So electromigration, that's also a very good question. Thank you. So electromigration is of concern nowadays. It is also considered as a possible cause of the so-called silent data corruption that is of big concern nowadays. So there are basically microprocessors or even servers that fail in the field with no sign before, without understanding actually what's going on. And electromigration may be a cause. So it's a problem from any circuits, whether they are old, which I assume means is in the sense of aged, and as well as we call fresh devices. So electromigration is likely if there is a high current density and high temperature. So depending on the application of our electronic circuits, they may be more or less vulnerable to the taking place of electromigration. And there is this was a problem since tens of years, but it's becoming again nowadays of major concern, also because in scaled down technology and integrated circuits, it is becoming more and more likely. And it can be a problem for of course, old circuits, in the sense, I assume, age circuits, but also the fresh one. And if electromigration is added to aging, I would assume that there is That's a very good question and idea. I think there will be definitely amplification of the problem, because both of them may cause a delay of the circuit. And so probably the two will add together. I cannot predict now in which way, but for sure, I can expect, because this is something I pretty new and interesting, that electromigration will make the effect of aging worse and vice versa. So there will be an additional slowdown of the circuit, because electromigration typically causes the so-called bridging faults that I mentioned before, and one of the impact of bridging faults is also to slow down the circuit operation. And so at the end, if you consider a signal data path, it may create the generation of incorrect data. Or bridging faults may, when activated, they may create, depending on the value of the bridging resistance, may create themselves a logical error also within a combinational logic. But the delay effect is always there, and so again, they could put at risk the reliability of our system. That's a very good question. Thank you.
Thank you, ma'am. We will take one more. I am reading out the question, ma'am. Are predictive maintenance of electronics paradigms being considered for incorporation into Metaverse hardware?
That's also a very good question. So I think so. Predictive maintenance is typically considered at the industrial level very important, and AI enables to implement predictive maintenance in some cases. And so I think that this, let's say, feature offered by AI will remain as a key part, as a key component of the metaverse, because again of its industrial application. Predictive maintenance enables also to increase safety, and for sure it enables to plan the maintenance. But first of all, I think it's an approach. They are approach that enable also to increase safety. And so I think it's a very good question, and I think it will remain as one of the key components of the metaverse. And the stronger integration of these tools and the real reality, let's say, would make, probably with respect to what we already have nowadays, predictive maintenance more efficient, and probably will favor its widespread adoption in a wider range of application with respect to what we already have nowadays. Very good question. Thank you.
Thank you, ma'am. One more question. It's coming up one by one. How often would these errors occur per square centimeter of chip area?
That's also a very good question. The answer, unfortunately, I think it's, I mean, this is a very important question. And as far as I know, companies are worrying about this a lot. But it really depends on so many aspects that, as far as I know, no one has been able to answer this question yet. So they may occur, these soft errors are very likely to occur if the memory elements are affected by transient fault or single event transient, we want to call them. And this is why memory elements are often protected. But again, there is the issue in the perspective of such a wide application of AI and so many decisions taken based on AI, to be sure that the protection level that is provided is sufficient to guarantee the reliable execution of AI with no impact on safety at the system level. And so this is still subject to research, and the prediction is difficult because it depends on the particular kind of application, and we can have any kind of application, given the widespread adoption of AI. It strongly depends on the technology also. So which specific kind of technology is adopted. It depends on the design of the electronic circuit. So let's say the generation of these soft errors depends a lot on the design, on the frequency of the clock. So it depends on parameters, let's say, that are under some sort of control for the company that is fabricating the chip and that is designing the chip, but also depends a lot on environmental conditions, so which are not under control, let's say, or unpredictable. Also depends on actually the application which is running, because there is a dependency on the value of the other logical value of the other signals. And so it's a very difficult scenario. I hope that given all the research in this field and given also the pressure from companies to be able to predict how likely it is and how often these faults may occur, we will be able to find a model that is accurate enough and general enough to answer to this question. So it is a very good question. It is a very important issue, which is under research and with lots of interest also from companies. But as far as I know, there has not been a general solution that has been found out yet to answer this question, because there are too many factors that influence the likelihood of this occurrence of faults. What we can see is that they occur, and so let's say I speak myself as everyone working in the field, we are worried about them. We try to develop solutions to protect the chip with respect to them. How to figure it out clearly how much often they can occur and when and so on, of course, will open the way, pave the way to new kind of solutions, probably cheaper than the one that which are under development right now. But as I said, that this is a very good question, still, I would say, object of research. And to be honest, I don't know if you could ever find out a general answer that could apply for any circuit and any kind of application. But the question is very good and very timely. Thank you.
Thank you, ma'am. The next two questions we are coming from our in-house, that's Professor Lance and Professor Cookjin. Professor Lance has asked, I am reading out the question. Obviously, HW and AI in reliability is a major concern. If critical services relating to life and death or national security are involved in Metaverse, are there any such applications for services are already in exist in Metaverse?
Thank you. This is also a very good question. And so how about, yes, such application service exists in the Metaverse? So that's a very good question. And again, it really depends. So what we consider as Metaverse, that's why I was talking about future Metaverse. So right now, I honestly don't see that kind of integration, synchronization, especially and cooperation from all these tools and services that are already provided by diverse companies and the real world and among them. But as far as I know, there are already, let's say, several kinds of services that are provided for free as well as by payment from different companies that could be used also, for instance, for safety critical applications, in the sense they could help to find, I don't know, for instance, especially in the medical field, they could be adopted to find out in a quick way, maybe a list of disease and diagnosis. There are even services that are used in the legal field to make a quick search of everything that can be found on the internet. And we are talking a lot nowadays, however, about the explainability of these tools and about the correctness, let's say, or the trustworthiness of the answers that are given. So there are several services, especially for personal assist in the form of chatbot that are used for digital personal assistants that are already available for free or paying. There are several concerns about them, their explainability and the fairness and the correctness of decisions and the recommendations, let's say, given. And the idea is that in the future metaverse, all these different separated capabilities will be harmonized, will be integrated, and of course with a guarantee of reliable decisions, a guarantee of data protections, all these issues that would need also, I think, regulations. And so in the future, there will be integration of these still separated services that are offered by different companies. The idea is that they will be harmonized and there will be an increased integration with the real world. And I think that one of the key points of this future metaverse, that the predictions are that it will will happen by 2030. There will be really a change, a significant change, and AI will play a key role from this perspective, a significant change in the way we can interact with these tools. Right now, it's mainly through video. We're doing it right now. But the idea is that in the future, it will be in a more inclusive and intuitive and natural way to communicate, so that even people with, for instance, disabilities could really interact in a natural way with the metaverse. Right now, we are still limited, typically, okay, we also have voice command, gesture, not that much. So we typically are interacting with our digital world, we can say, through a screen, through a screen. And in the future, the idea is that it will be more more inclusive and in a more natural way in the interaction, so that the integration of the digital and real world will become stronger. But thank you very much. This is a very good question.
Thanks, ma'am. The next is from our Cook-Chin. The question is, do you expect more SE problems in the neuromorphic devices such as RRAM and MRAM?
Very good question. Thank you very much. So concerning this kind of memories, honestly, I'm not aware about analyses that have been done for magnetic RAM and resistive RAM from point of view of errors, and I'm trying to think, but honestly, I don't know the answer. I didn't work it on this personally, and I'm not aware about analysis for soft errors. We worked on resistive RAM, but analyzing bridging faults. From the point of view of soft errors, probably, I think maybe but anyway, I didn't address this issue, so I prefer not to answer. That's a very good question. And that's a very good, let's say, research topic to be addressed. So for resistive RAMs, as far as I know, it was not a RAM, it was not analyzed. I'm trying to think. I may say the situation will be different because, as far as I know, this has not been addressed also by colleagues and not by me. And so thank you for the question. This is a very good question and could be the topic of future research from people working in the field. Thank you.
Ma'am, one last question, and after that we will end the question answer session. I'm reading out the question. In a real-time AI system, which might not be a safety critical application, what are the indications to be noticed or detected for the occurrence of the AC or BF or other faults that breaches the AI reliability and safety. What role Metaverse plays in this case?
Thank you very much. Let me try, I'm trying to read again, sorry. So the question, I think, is, that's a very good question. So if we have a non-safety critical applications, I would say that if it's not safety critical, one may say we don't care about faults affecting the hardware executing the AI. But honestly, I think we will have to worry for any kind of application, because if we think about, so also in the perspective of the metaverse, but not only for that, but let's talk about the metaverse, this integrated digital and real world. So the role played by AI, which is enabling our accessibility to the metaverse, enabling lots of service, will be based on using AI in the metaverse. If we are thinking about a widespread adoption of this service, I think the reliability and safety will be critical for basically any application, because if you think about, we were talking before, thanks to some of your questions from the audience about predictive maintenance. Well, if it fails and gives the wrong decision, even if it is for the production, I don't know, or for even in the production line, it means that okay, maybe we correctly, as you said, it will not be safety critical in the sense that the life of no one could put a risk, but even that you don't know. But anyway, it will be a failure of this system, and at least a big economic loss for the company that in turn may result in problems for people working for the company, for instance. But if you think, for instance, predictive maintenance of an autonomous robots, of course you need to worry about that. Even if the robot is simply moving objects in an industrial environment, and let's assume it's not interacting with humans, but again, if it's not maintained and if it's getting to work incorrectly, it will create disasters, and again, at least there will be an economic loss. So I think that in addition to the safety, that's a very good question, and I believe that in addition to safety critical applications, just like I don't know, the airbag control in a car, for any kind of application, if you're thinking about a widespread adoption of AI, the reliability will be of concern, because whatever, if the AI will make wrong decision, you can have consequences that maybe are not so, would not put a risk at the life of people, but you could have indirect consequences to the wrong decisions that, okay, will not put a risk life of people, but at least will create serious problems. Let's assume, as in my examples, you cannot, you are inhibited a financial transaction, okay, it is not a big a safety risk, but anyway, it's a significant unavailability of a service, maybe I'm not able to pay the hotel room, and so I'm not enabled to leave, I lose my flight, I will not arrive at home, and maybe at home someone is waiting for me and is my presence. So just to invent, but I think in addition to the safety of the application, which depends on the application, the widespread usage of AI in itself will mandate the need for its reliable operation, because I think so it will be important to answer your question, the safety, and so to deal with soft errors, breaching faults, possibly compromising the reliability of the AI, and the safety. I think that the reliability of AI, if AI as it seems, will keep on being more and more adopted, will be critical for any kind of application. And its role in the metaverse will be very important, because, for instance, AI is the key technology that enables the service that will be shared and offered in the metaverse will enable, it seems, the accessibility to the metaverse. And so even that maybe for a service that is not safety critical, but anyway, maybe is important for our lives from different point of view. So I think it will still be a problem. And so thank you a lot for your question. Very good question.
Thank you very much, ma'am. Thank you very much for the wonderful session that we had. And it was nice meeting you. We now move on to our next leg, that is from question answer session to the valedictory session. We are moving on. For the valediction, we have Mr. Deepak Mathur, and I have the privilege of introducing him to the audience also. Mr. Deepak Mathur has served as the director of IEEE Region 10 in 2021 and 2022. He is presently IEEE Vice President-elect of Member and Geographic Activities, and he will be serving as the IEEE Vice President of MGA in 2024. Deepak has also served in various volunteer leadership roles within IEEE at Section, Council, Region, and MGA. Previously, he was IEEE India Council Chair in 2015 and 16. Mr. Mathur is a former Chief General Manager at ONGC and has more than 37 years of professional experience in the field of electronics, telecommunication, IT infrastructure, and has held various engineering and managerial positions during his career. He holds a Bachelor of Engineering degree in Electronics and Communications from IIT Roorkee and an MBA. He has also completed Advanced Management Program from IIM Calcutta. In his IEEE journey, Deepak has been the recipient of various IEEE recognitions and awards, including the prestigious IEEE Region 10 Outstanding Volunteer Award, IEEE MGA Achievement Award, and IEEE India Council Lifetime Achievement Award. He is also a member of the highly acclaimed International Honor Society IEEE HKN or Eta Kappa Nu. With these words, I welcome Mr. Deepak Mathur to deliver the valedictory address and propose the vote of thanks. Mr. Mathur, please.
Thank you, Sanjay. Thank you, Sanjay. Thank you very much. And thank you, 10 Talk team, for another great session. I'm really grateful to Cecilia Metra for accepting our request and delivering such a splendid talk on reliability and safety challenges for the AI hardware to enable the future metaverse. And the question and answer session shows how much interest our participants were having in this particular topic and how much benefit they got. That I'm sure participants had very useful information from the world leader in this field. So thank you, Cecilia, for joining us on this 10 Talk series. And today's topic, I think, is very relevant to today's fast-changing technical scenario. And Cecilia has explained many aspects very nicely, and that reflects her grasp of knowledge and experience on the subject. So Cecilia has already been introduced, is part of the Italian National Research Center on High Performance Computing, Big Data and Quantum Computing, and she is also the part of Italian research project on security and rights in the cyberspace. And many thanks, Cecilia. We are truly honored to have you in our very popular flagship program, where we invite world leaders and technical experts to deliver talks on the trending topic. And 10 Talk webinar series is perfect example of collaboration and team effort within the region 10. So we started this program in 2021 and invited experts from different countries. And this is also an example of finding opportunities from challenges. And you all know that in 2021, we were passing through an unprecedented and challenging time. In true way, we have erased boundaries. Our speakers are from different parts of the world, and so are our participants. So R10 Talk is a joint effort of Region 10 committees, where 5 committees, namely Industrial Relations, Professional Activities, Young Professionals, WI, and Student Activities, have joined hands together to spread awareness on trending topics to the benefit of the community and to the benefit of IEEE members and even for the non-members. It has been very successful program, and talks by experts are well appreciated all over our region and even from other parts of the world. So I thank all organizers for their efforts in organizing this talk and taking our 10 Talk series forward. And I would like to tell you that the performance of our region is excellent. And let us continue our good work and make volunteering a joy, and let us organize more value-added programs. And I would also like to thank Professor Lance, our Region 10 Director, for coming out with a very good member engagement program and very thoughtful activities for Region 10. And I really feel proud of Region 10 volunteers and their involvement, dedication, commitment, and contributions, and that have always been outstanding. So with this, I conclude and wish all success to 10 Talk series and to Region 10. Thank you very much, Sanjay.
Thank you, sir, and thank you, ma'am. All those who are present today, you can give us a feedback. We will be very happy to have that. You can scan the QR code and just put your comments there, what you want. So I can assure you that we won't disappoint you. And we are very much eager to have your feedback on the topics as well as what you want really. Our next webinar, that's IEEE Roadmaps. We will be having it after the Section Congress. And speaker is none other than Professor Rakush Kumar, and date and time to be announced in consultation with him. So we are waiting for a date and time from him. Thank you, everybody. And it's time that we should wrap up. It's what Mr. Deepak has said, it's a joint effort. It's a collaboration between IEEE Region 10 Industrial Relations Committee, Professional Activities, YP, Young Professionals, Humanitarian Technology, we, Student Activities, and Life Members.
Thank you very much. Bye-bye.
Thank you, ma'am. Thank you very much. We just wait for 1 minute. We will have a group photograph, and thereafter we can wrap up. So you can connect with us on LinkedIn, Facebook, and everywhere on the social media. In fact, today's event has been shared on Facebook page live. So you can have it, and it will be again put in YouTube. So you can have all these sessions sometime later on this social media platform. So please do connect with us. Stay tuned with us for our next webinar series, and we will be shortly coming back to you. Thank you very much. So please wait. We will have a group photograph. I would request everybody to switch on their video cameras so that our group photograph, yes. Akila, can you just help us in taking that group photograph? Thank you. Veronica, your camera, please. Thank you. Thank you, everybody. We wrap up the session.
Thank you so much.
Hope to see you very soon in next month.
Yeah.
Thank
you very much.
Bye-bye.
Thank you.
Bye-bye.
Thank you.
Bye.
Thank you. Bye-bye.
Bye.
Bye.